Welcome to Season 2 of the Coherence Times, where we bring coherence to the entangled world of quantum computing. I'm your host, Ryan Mandelbaum. Every other week, I'll bring you stories about how scientists, developers, and businesses are making quantum computing a reality. We'll explore new research and development, highlight the latest advances in the field, and see how users are trying to extend quantum to real-world problems. Superconducting quantum processors are incredibly sensitive. They need to be protected from outside interference and cooled to temperatures near absolute zero, while still being connected to a bunch of control electronics. So as they continue to scale, the systems that support them have to scale too. That's why IBM is developing modular cryogenic platforms designed to connect, operate, and scale quantum computing systems. These will be required for the future of fault-tolerant quantum computing, where modular processors will work together to run larger quantum circuits. So, I've invited two guests to help me understand the importance of cryogenics for quantum and how IBM is preparing quantum hardware for this sort of scaling. First, I'm joined by Matt Hollister, IBM Quantum's head of cryogenic systems engineering. Matt has helped to shape the infrastructure that supports increasingly large and capable quantum computing systems, including our new modular platform. Also with us today is Allie Lindler, a cryogenic assembly engineer who works on the design, integration, and operation of IBM Quantum's cryogenic systems. Matt and Allie, thanks for joining me. All right, so Matt, let's start with the basics. For our listeners who maybe don't know that much about superconducting quantum computers or about cryogenics, why don't you tell us about why these processors need to be held at such cold temperatures?
Okay, so superconductivity is inherently a low temperature phenomena. It occurs in a number of different materials, some of which are elemental metals, some compounds. There are some exotic materials that display superconducting properties at relatively high temperatures. There's a class of materials called high temperature superconductors, but even there, it's high temperature in this context is still cryogenic. The devices and the materials that are generally used in superconducting quantum devices are more of the very low temperature variety. So we're talking about phenomena that only really appear when you're operating down in the sort of 4 Kelvin temperature range, which is at around minus 269 degrees Celsius. Out with the superconducting quantum devices specifically, quantum phenomena in general is something that's inherently quite unstable. So to maintain the quantum phenomena that we're actually using in these computing devices, it helps to operate at very low temperatures in order to reduce the phenomena of noise coming in from the environment. Any heat that enters these devices is enough to destroy the quantum phenomena that we're actually relying on in the processors. That's something, though, which is true beyond superconducting quantum computing. So even non-superconducting devices will often benefit from operation at cryogenic temperatures, although maybe not quite such deep cryo as we generally work with.
Negative 269 degrees Celsius is that sort of 4 Kelvin range. This is very cold. Can you give me a sense of how cold this really is?
The typical temperature that people refer to is deep space, which is sort of slightly below that temperature. It's kind of hard to put it into a physical context in terms of what we would experience in everyday life. So that is a very difficult one to answer. However, the 4 Kelvin temperature where a lot of these phenomena start to turn on, that actually is the temperature of liquid helium. So this is not something that you're going to carry around in a carton or something, because it is so cold, it evaporates very, very easily. People are probably used to seeing liquid nitrogen as a cryogenic fluid. There's sort of the typical internet demonstrations of people plunging items into nitrogen and freezing them and causing them to shatter. That is, in terms of the temperature scale, that's about 20 times warmer than the 4 Kelvin temperatures that we're talking about for helium.
I want to just make sure that the sort of listeners understand that there's like two temperatures that we're kind of talking about here, right? We need to first get to the temperature that things are superconducting at all, which is already a very cold temperature. But then we get to sort of this quantum, we have to push it even cooler to this sort of millikelvin scale, essentially, so that not only do we have access to these quantum phenomena, the superconductivity, but also access to actually be able to control it without all of the noise that might ruin the quantum computation, right?
Yeah, that's actually a good way to think of it, Ryan. In reality, the refrigeration systems that we tend to use are really multiple refrigerators working in unison. And you can't go from room temperature to these very cold, near absolute zero temperatures in a single refrigeration system. So the actual technology we use really is a cascade of several refrigeration technologies to access these very deep cryo temperatures.
So before we get into the construction of the actual hardware, maybe we can talk a bit more about like what it is that we're trying to protect against in this quantum realm, Allie. Can you tell us about what it's like to be a quantum processor at these cold temperatures?
Yeah. So to be a quantum processor in the very bottom of your system, you think about an OVC initially. So it's a dark space that your cascading cryostat sits inside. The processor is primarily trying to be shielded from things like thermal radiation and electromagnetic radiation. So the ways that we kind of do this are we shield around the processor because electromagnetic and thermal radiation can actually act like light, and it can kind of bend around crevices inside of the computer. And if there's something like a room temperature photon that could kind of travel from room temperature all the way down to the cold stage where your processor sits, there was a colleague that actually described it to me like a lightning strike on your payload, which I thought was pretty neat. And it's very amazing that something as simple as a photon could strike that payload and cause a decoherence of sorts, given that the pulses that go inside of the computer are so much smaller than room temperature photons.
I see. So even if we have this chip held at this negative, 273 degrees Celsius, basically near absolute zero Kelvin, a room temperature photon sneaking in, it really can do some damage to your computation at the very least.
That's why we're very precise in how we machine things like shields and stuff like that to try and keep those photons out.
So let's work together to understand what these things are and how they actually work. I think, Matt, you got us started. Can you tell me about this cooling in successive stages? What is this and why does it work the way that it does?
So the story here really starts in the early 1900s. Around that time, there was a lot of interest in driving to lower and lower temperatures, and there really was a race of sorts amongst a number of scientists in Europe and North America to liquefy gases at progressively lower temperatures. So things really start to get interesting in about 1908 when helium was first liquefied by Owens working in Europe, and this was the first time that sort of low temperature boundary, the sort of 4 Kelvin boundary, had really been reached, because every other liquefied gas exists at much higher temperature than that. This was also intimately connected with the discovery of superconductivity itself. It turns out that mercury superconducts in that temperature range. So being able to achieve that 4 Kelvin temperature limit also allowed for the discovery of the superconducting phenomena in the first place using elemental mercury. Following from that, there were further experiments that sort of pushed the low temperature limit down to about 1 Kelvin. And that's still a temperature that you can achieve using regular off-the-shelf helium-4, which is the common isotope of helium. And at about that time, there was some discussion of, is it possible to sort of achieve even lower temperatures? It turns out you can't just by using simple liquefied gases. But in the early 1900s, around the mid-1920s, there was a new class of refrigeration technology was invented, which relied on ordering and disordering of magnetic domains in salt materials, and that allowed a push down a little lower in temperature. And that was the first time that it was really possible to access these millikelvin temperature regimes. The problem with that technology is that it's inherently discontinuous. So it's great, but you can't operate something for a long period, which makes it challenging to do any sort of computational process or similar where you really want to maintain that temperature for very long periods. So it wasn't until helium-3, which is the rarer, lighter isotope of helium, was first identified in 1939, that it really became possible to achieve these millikelvin temperatures continuously. The base technology that we use is a type of refrigerator called a dilution refrigerator. And that relies on a mixture of the two primary helium isotopes, helium-3 and helium-4. But what it does allow you to do is reach these millikelvin temperatures in a continuous process. So that was a real breakthrough in the early to mid-1960s, where you were suddenly, for the first time, were able to achieve these millikelvin temperatures continuously. Now, we'll fast forward a little way. The dilution refrigerator technology has been used for a lot of different applications in fundamental physics, a lot of them connected to both studying superconductivity, but also the development of superconducting devices, such as the quantum processors that we use in our quantum computing systems. The way that the refrigeration process actually works turns out that if you cool a mixture of the two helium isotopes to sufficiently low temperature, because of the different quantum mechanical properties of the two molecules, the two atoms, they actually spontaneously form separate phases. So a little bit like oil separating from water. But an important difference is that unlike oil and water separation, you don't get a complete separation of the two helium isotopes. What you actually have is one phase which is essentially pure helium-3, but then the other phase is mostly helium-4 with a very small amount of helium-3 dissolved in it. And it turns out that if you encourage helium-3 to move across that phase boundary, it produces a cooling effect. And that's what the dilution refrigerator technology is reliant on. Now, as I mentioned a moment ago, these systems really are several cooling stages cascaded together. The dilution refrigerator part really only operates below a temperature of around about 1 Kelvin. So you have to provide some sort of cooling between room temperature and that sort of liquid helium temperature range at a sort of the midpoints of the refrigeration system. Traditionally, this had been provided just with a bath of liquid helium. But an important innovation in the late 1990s into the early 2000s made use of a mechanical refrigeration technology, or I should say several types of mechanical refrigeration technology that allowed you to reach temperatures around 4 Kelvin without needing that bath of liquid helium. So really, the refrigeration technology that we use now as our workhorse is a 4 Kelvin refrigerator, which is pre-cooling that dilution refrigerator to reach down into the millikelvin regime.
Got it. And that makes sense because it does a couple things, right? Obviously, the most important is it reduces, you can't have these lightning bolts, photons that Allie described shooting in there. So we cool in successive stages. I know there's thermal stresses, things like that. And then I actually wanted to bring back something from the previous season that I thought really described the evaporative cooling here really well, which is it's almost like you have like the sweating, right? It's literally like a little evaporative process of taking heat from one helium isotope, the helium-3, into the other helium isotope, the helium-4.
So yeah, it's exactly analogous to an evaporation process.
And then, Allie, can you tell me about, I don't think listeners will be able to hear this, but Allie's sitting in a lab with all of these refrigerators right now. And I think it's really amazing. And I want to actually hear from you, like, walk us through what it looks like, what it sounds like, and maybe how these fridges are actually built, right? I mean, they're gorgeous chandeliers. Can you get us through a bit of the construction piece?
So in terms of walking into the data center, you kind of walk in and you hear these pulse tubes. So these pulse tubes sit on top of your cryostats. So you kind of just walk in, you see a lot of cabinets. We have different cabinets for telemetry. We have cabinets for gas handling. So telemetry kind of puts our systems onto network to where clients can access and use them. We have cabinets for our room temperature electronics. So we have cabinets that go, that give communication from your telemetry to your RTE. We also have cabinets, like I said, that are for the gas handling system. So the way that you can operate and maintain a cryostat is through this cabinet that's known as the GHS. So what this has is essentially a bunch of turbos. It has a bunch of pumps. It has a PLC interface to where you can access valves, pumps, your turbos, everything else. And that GHS has a line, 2 lines actually. You have a still line and a condensing line that run kind of over the ceiling, and they kind of go and attach to the chandelier itself. So that chandelier hangs in our data center. It looks like a cylindrical can, which is your outer vacuum can. And the chandelier sits inside.
Okay, so we have this chandelier, we have this fridge, this cooling system, and now, Matt, I know that we need it to be bigger than just one, right? One of these chandeliers, maybe they hold a chip that's got like 100, 200 qubits or so. But I think one thing that's really amazing is this discovery of this modularity that we can start to do. Can you tell me a bit about that? Like why do we need to build modular quantum computers, and how do we build a modular fridge?
So the real motivation for going to a modular architecture is we know we have to build systems with higher qubit counts than we're able to do at the moment. So depending on who you ask, there's numbers of anywhere between a few thousand up to a few million individual qubits in a useful quantum computer. To fit that into a single cryostat is very challenging. While it's possible to build large cryostats, and here we're talking much larger than the systems that we've historically used up until this point for our deployed quantum systems, it doesn't make a lot of sense to try to build a single big system to support computers at the scale of what we're talking. It's also very inflexible to take that sort of approach because you have to design for a particular size system. And if we decided we want to make the system 50% larger, there's a lot of inefficiency in then having to re-engineer everything from square one in order to accommodate that. So our approach for these very large future systems is really to adopt modularity at all levels of the stack. The technology processes associated with the production of the quantum chip, of the electronics, as well as the infrastructure such as the cryogenics, naturally lends itself to a particular maximum size, and that does not necessarily match to where one would want to be if you were to try to build this as a monolithic system. So really at all levels, everything in our scaling plans point towards making the system modular. In the cryogenic space, at least from the point of view of systems operating at millikelvin temperatures, that's not something that's really been done before. Certainly people have experimented with large monolithic cryostats in this sort of temperature range, usually for a specific application, such as a specific one-off experiment. But this field where we're talking about wanting to build many copies of our systems to couple them together to make this expandable modular system, this actually is quite a unique and new technology space that we're operating in.
And Allie, how do you actually make a fridge modular?
Yeah, so we have in the lab right now, the way that we make these guys modular is we have chambers. So these chambers are kind of customizable to however you want to orient whatever system or position that you're wanting to create. So the way that they work is they almost look like a bank vault to where they have doors on 4 sides. And then you can take off doors or add as you please, or as you continue to build more modular systems, putting more cryostats inside. So 1 cryostat per 1 chamber. You look inside. If you were to open the doors with it fully assembled, you would actually just see a very shiny MLI blanket and shields. So MLI actually protects your processor, reflects a lot of that initial infrared and electromagnetic radiation and things like that coming inside. But these modular systems actually have panels. So for the shields, you have front panels to where if you wanted to do a servicing of sorts or you wanted to access the wiring inside of the fridge, you can actually just take the front panels off simply and have access to your processor. You have access to your wiring. You have access to essentially everything, which is much different than your standard cryostat to kind of where it hangs in a frame and it's a cylindrical can. And if you wanted to, access the system, you'd have to take the OVC cans off and you'd have to take all the cans off to kind of access. But the way that it's truly modular is that we have the ability to have as many chambers that we need per system or how many qubits that we want or that we're looking for. So the systems actually have bridge shields. So the way that you can kind of connect these systems together is by both connecting them under vacuum. So both sides of the chamber have either an O-ring groove or they have an O-ring receiving surface to where you can almost winch or push them together and apart. And then from there, you have bridge shields that allow for essentially a connection for your processors to be run through and in between. The shields actually have a small gap in between. So the shields from one cryostat to the next do not actually touch, but they are coated in a dark material that allows for light tightness and having the tunnel, so to say, or bridge to be able to connect multiple payloads together in multiple cryostats, which is thus making it modular.
So I like to imagine this because I have limited mental capacity. I imagine kitchen refrigerators, and I imagine you have a big one, and then you get increasingly small, and then you have a very small kitchen refrigerator in the middle, and that one can miraculously cool your lunch to basically absolute zero. So are you essentially saying that, and if it's better to imagine that you were going from top to bottom, and so the innermost one is both in the middle and also at the lowest of all these refrigerators. The freezer's on the bottom, like many for one fridges and freezers you buy. And so essentially there's like tunnels that can get connect in these little, you can imagine like a whole rows and columns of these stacked, or maybe just rows and aisles of these refrigerators in the way you might imagine a superconducting or a supercomputing center with lots of racks. And so basically you're saying that there's like tunnels between those innermost refrigerators that we have to do a lot of hard stuff in order to get them all connected?
Yes. Well, I wouldn't say hard stuff. I would say you have your cryostats assembled. And it's actually the modularity of it makes it not too difficult to actually put multiple systems together with the bridge shields. So a good way to kind of think about it is, like you said, you have the freezer like as the smallest and the most cold. But you have that bridge, you have a bridge for each thermal shield stage. So you have a bridge at your still, your 4K, and your 50K. And same for the modular cryostat for the system that sits right next to it and next to it and next to it. So they kind of continue on in a line. And then you have indoors or end caps on both ends. And you can cap off or close your shields on your ends. And if you ever wanted to change that, you could just simply, like a refrigerator, open the door and make your changes and connect them all together.
Amazing. It's like going to the quantum grocery store and they break
It's
the
amazing.
fridge.
It really
So-
is like a beautiful piece of engineering. It's incredible.
And I know that this is not easy. I think when I talk about it in these analogies, it doesn't sound as hard as it is. So I maybe want to talk to Matt about the project plan that actually got us here. How do you go about sort of going from building what is, maybe people don't understand that dilution refrigeration has actually been around for so long that we almost think of it as like borderline off the shelf technology, to now what we're doing is building this big modular crazy fridge designed just for modular quantum computing. So I'd love to hear a bit about that, Matt.
Yeah, it's possibly a sort of oscillation in the way the technology is developed. As we discussed before, the dilution refrigeration was first demonstrated in the 1960s. But for a very, very long time, these refrigerators only existed in university labs, essentially for fundamental research. Part of the issue there was that there wasn't a major commercial application for the systems. A lot of people would build and operate their own fridges, and there was a lot of sort of esoteric knowledge that only existed in these university labs. Quantum computing, I think, was the first major technology driver that actually brought the fridges out of the lab and more into the hands of companies that had the impetus to develop a more robust, a more industrial type product. And as I say, a lot of that was driven by companies like IBM that were pushing to develop the superconducting and other quantum computing technologies. Where we are now, and traditionally what we've done with our systems to date, is that we've taken a relatively small off-the-shelf cryostat, which is the sort of classic cylindrical chandelier that appears in any number of publicity photographs. And fridges of that sort of scale are capable of, depending on the exact architecture, they're capable of supporting anywhere up to low thousands of qubits. IBM itself has demonstrated over 1,000 qubits operational in one of those standalone fridges. The issue then, though, is to go larger, you have to have a way by which you can couple multiple fridges together. So we have separately developed the capability to connect the individual quantum processors together. But you still have to get signals from each quantum processor out to room temperature. So that's where a lot of the chandelier hardware that you see, really, that's all wiring to control the processor and read out the signals. So that becomes the driver, really, of how dense you can make these systems. And it turns out that a good size module, at least for our readout architecture, is slightly larger than the sort of commercial off-the-shelf fridges that we've been using up until now. These systems actually we still use, so we're really developing the next technology here. Versus making some single large system. We had experimented a little bit with making larger systems. In the early 2020s, we had a project called GoldenEye, which aimed to build a large monolithic refrigeration platform. And while that project was largely successful, and spurred a lot of development in the in industry to make larger fridges, ultimately we determined that system, the building block was really too big. There was some ability to do modularity, but really the individual block was too large. So following the GoldenEye project, we then started to explore some other options for smaller, higher density modular cryostat configurations. And that morphed into what became known as the Union project, which is the modular cryogenic system that we're in the process of developing in our lab. And really what Union represents is a building block which is suitable for installation in data centers. So it's about the size of a large server rack, but it has the ability to be coupled in such a way that you're also able to make these connections at the level of the quantum processor, so that you can string one processor to the next and make these ever larger systems.
So it is going to kind of be like a supermarket of quantum processors, if you imagine the freezer aisle.
I prefer to think of it as a server rack, but yes.
The server rack of quantum processors. Anyway. So Allie, this is a hard project, I assume. And I would love to hear about some of the challenges, like when you first were brought into this project and had to see what we're doing and how we're moving from these single fridges and monolithic fridges into this, server rack of fridges. What were some of the first challenges that you saw?
Yeah. So we kind of started, I joined pretty much when this project, the parts started actually forming and started coming to IBM. So starting out, it was initially a lot of site preparation. So making sure, even little things like thinking about how are we going to take this cryostat and put it inside of this modular chamber. Like we need the infrastructure to be able to do things like this. So it was a matter of getting the infrastructure here on site to be able to do that. And then going from actually receiving the first ever, there's a lot of good people, and I've had a lot of help here in Poughkeepsie, and in Yorktown as well. It's really been a team effort in terms of getting everything here, and then from getting everything here to reviewing documentation and kind of figuring out exactly what goes together and how, and not only reviewing documentation to see the assembly process, kind of going through the motions yourself and kind of seeing like, hey, maybe we would like to do this way instead of another way. I think a decent example, you're not only kind of taking new parts and building them onto a cryostat, you're also having to deploy, set up, and maintain an actual physical cryostat that IBM is more used to. In a certain way, the cryostats are similar in terms of configuration. The modular cryostat has different plate shapes, but it's a similar process. But it was a lot of trial and error. And there were some times where I kind of had to take what I have learned in terms of thinking about all of these processes and things that can affect the fridge, things that can affect the processor. I kind of had to take those into consideration and kind of practically apply them to what I was doing here. And there were times where I would get stuck, and having brilliant and smart people, great leaders like Matt, who I could feel like, hey, Matt, I would like to have your opinion on this, and kind of working with the designers, working with the people that kind of move this project forward and getting the parts here and actually giving that final push to have a fully functioning system. And having to troubleshoot things sometimes, because you can have one thing on paper, but it can get here, and it can be something entirely different. And you have to kind of take the science fundamentals that and kind of practically apply them to build a system that is functional.
Can you give me an example of that, like the zip ties and dental floss for this project?
So I wouldn't say dental floss here, not yet. I would think a good example would be the shields. So kind of how I touched on, infrared, electromagnetic, light tightness in shields. There were some times where, tolerances aren't always perfect, and vendors, don't always send you the perfect bored through hole or the perfect pin nut in the perfect spot. So there were some instances kind of where you would kind of put the shields on and you'd have a problem of, hey, there's a gap here and it's not light tight. Or you'd have another issue of, a vendor making a part and its protrusion was more than you expected and it's trying to short out to a different stage, which that would cause the cryostat. You would most likely not be able to condense the system or cool it down to its base temperature. So things like that, we kind of had to, you talk to the designers, talk to Matt, talk to everybody and kind of see, hey, look, let's have a conversation about this, or let's try and figure out a solution. So like for the shields, copper tape has been a very good friend of mine, in terms of filling those gaps. So they're not in places where you can't necessarily make up for them, on a prototype system. Copper tape has been a great resource. Our Poughkeepsie model shop has also been a wonderful source in terms of, we want to modify or cut off this lip here so it doesn't short out to a stage adjacent. So like the still stage shorting out to the 4K, or 4K shorting 50, etc. So we've kind of had to take some innovative ideas and try them out. And, it's a prototype. So there's been a lot of learning involved, but there's been a lot of smart people on the project that have kind of worked through these problems and tried to improve the system as we go.
And then maybe Matt, from your point of view, looking at this at the project level, I mean, were there any surprises, like lessons learned or things that while you were watching the team put these things together, you maybe had to make some pivoting or do things differently than you expected?
There probably were a few instances where we had to adjust what we were doing, but a lot of that was in response to changes in other parts of the technology. Um, One of the goals for wanting to bring the design of the modular system actually within IBM rather than outsourcing it to a vendor was that it allows us to execute much faster, because the field is developing very rapidly. There's a lot of developments that are happening in other parts of the system, such as the processors, such as the readout wiring. So having control of the design ourselves and being able to respond to the changes in other parts of the system really has allowed us to have a system which is much more closely tailored to, I think, to what we would look for going forward. That approach was relatively new for IBM Quantum as an entity, because previously, with the use of the off-the-shelf type cryostats, you were really designing other components to fit the existing cryostats. Whereas with this project, we've taken a much more holistic approach to the overall design, and the cryostat design really has been very closely in conjunction with other parts of the system.
Maybe to follow up on that, that kind of brings about this good point that we're in this era right now where quantum computing is not really a lab thing anymore, right? Is the actual clients and partners who are using them to do real things. And so, with that being said, how are you designing a dilution refrigerator to kind of meet that needs, right? To be this sort of commercial exterior to the commercial product that lives inside?
We've taken the approach of trying to maintain tight control over technologies that are relatively straightforward, but more specialized parts, such as the actual cooling system, that we leave with the specialists. So the core cooling system that we use in these cryostats very much looks like the commercial dilution refrigerators that we've used in previous systems. But really what we're doing is breaking up the different elements of the cryostat design and optimizing each one separately. So early on in this process, we went out to several dilution refrigerator manufacturers with a fairly broad technical specification, which laid out the key features that we needed in terms of the mechanical footprint, in terms of the refrigeration performance, all of which was based on what we understood of the rest of the hardware stack at the time. And then we're taking that piece from this vendor and another piece from another vendor and a vacuum chamber for another vendor, and we're integrating everything into a finished product. In the same way that we would take an off-the-shelf cryogenic system and then integrate our processor and our wiring into that, we've kind of expanded the scope of what we're integrating in-house. We have a lot of experience with making these systems robust because, as you said, this isn't something that lives in the lab anymore. That we are aware of the criticality of keeping these systems operating. So there's a lot of work has gone into and is still going into making these previously lab-based systems into a much more robust industrial type product that we can deploy either in our own data centers or to customer sites.
So I'm hiding this question at the end of this episode, and I don't know if I prepared you all for this one, but I know it's something that everybody actually wonders, and so I need to know the answer to it, and either of you are welcome to answer it, which is that if I have brought my lunch, which is a frozen burrito or something, and I would like to put it into the quantum dilution refrigerator, what would happen? And if it's not possible, why is it not possible?
Um, I think in principle it's possible. One place you might struggle is I'm not sure how compatible with high vacuum systems frozen burritos are.
That's exactly what I was going to say. I was, I was a little bit nervous about the vacuum more than I was the cooling.
So, like, basically what would happen is as you make it a vacuum, it would explode, right? That's just what would happen.
It would, yeah, it would give off a lot of gas, I think.
It would really ruin the expensive investment that you've made.
I think it might. I mean,
Or your
occasionally you
lunch.
find people
Or your
keeping
lunch.
you find people keeping soda cans in cryostats, but that's generally frowned upon.
All right, good to know. And I think that maybe let's just do the outlook then. I am interested more than what the refrigerator will do to my lunch is what the refrigerator will sort of do to the future of quantum computing overall. So maybe we start with Allie and just ask, what is where does it go from here? I mean, what are you excited about, and what do you sort of foresee as somebody working in this space?
For me, I'm a little bit biased towards the chemistry field. I do have a little background in chemistry, so my degree is in. So I look forward to, I read a lot of things that IBM has done in partnerships with different national labs, their different customers. I think about specifically for me, being able to model a molecule. So when I say model a molecule, like you could take, let's say you had X molecule that you needed to formulate a drug molecule to defend against. Just things like that, things that kind of benefit and help us in the world overall. Kind of seeing quantum computers almost outperform classical entirely. And in terms of the hardware, I think it's going to be really amazing to see right now looking at, two modular cells and thinking in the next couple years, that number will multiply greatly, and thinking about, the workforce that IBM will bring in. Having a computer with multiple logical qubits is something that is incredible to think about. Those are things that, I read about when I was in school and seeing it kind of come to life while I'm sitting here is I mean, it's incredible.
Awesome. And then maybe Matt, can you tell me a bit about the trajectory in terms of the cryogenics? Like, what are we going to have to do in order to realize the actual hardware that cools these fault-tolerant systems?
I think where we are at the moment really is only the first step towards being able to scale to very large systems. And we've demonstrated that the fundamental architecture works. We'll continue to grow the availability and the size of these systems in the near term. I think the major next challenge partly is related to the refrigeration in general, because in terms of the overall power consumption of the system, at least at the moment, the cryogenics is kind of a large contributor to the overall power consumption. And there's a lot of interest in driving the wall power of the system down. So that behooves us to both increase the efficiency of the cooling, possibly by adopting different technologies and pushing the development in the private sector space towards more efficient components in the refrigeration stack, but also it drives us to increase the density of our systems. The more qubits that we can pack into a single module also will reduce the overall power consumption of the system. Out with that, I think there may be a fundamental sea change going forward. What we're building now is sort of our best based on the technology that we have. But we're always looking for development, both in fundamental engineering, but also in the product space, the availability of different technologies from different vendors. So I think we'll be continuously innovating as we push towards the fault tolerant systems that are on our roadmap in the next 5 to 10 years.
Awesome. Well, cool. Thank you for taking us into this the cool world of cryogenics. This was super fun for me. I was delighted that we got to experience Allie sort of in the actual space and bring us into the world, even if we can't really see it. And Matt, thank you so much for the history. I really appreciate this one. This was super fun. So yeah, thanks again, guys.
Thanks very much for having us, Ryan.
Thank you again.
That's it for this episode of the Coherence Times. If you enjoyed the conversation, please be sure to subscribe wherever you get your podcasts, comment in the comments section, and share it with somebody who's curious about quantum. You can find us on Spotify, Apple Podcasts, and YouTube via the IBM Research Channel. And for more episodes, resources, and deep dives, please visit us at ibm.com/think/podcasts. I'm Ryan Mandelbaum. Thanks for tuning in. And remember, the quantum future isn't just coming, we're building it right now.